Hey there, everybody. Um, we're going to talk today about discrete probability distributions, and we're going to start off with some definitions first, and we're going to start off with a random variable. Which is a variable we often use a capital X to denote it for a single numerical value, and it's by chance. It's exactly what it sounds like. It's literally a random variable. Next up, we have a probability distribution. Of a discrete random function, and we're talking about discrete in this case. We've defined those numbers before. That means that it's countable. Random variable x provides values, and random variable, and so on. You can read this on your own. We often use a table graph or a mathematical formula. And random variables can be discrete or continuous. And for today's lesson, we are definitely going to be using discrete. In fact, all of Module 5 or Chapter 5 is discrete only. There's a couple of rules for a discrete probability distribution. The first one is we use P of x, and my number is a little off here, to describe the probability of a specific value of x. The thing is, when we add up all of the probabilities, all of them, it will always equal 1, meaning they will always add up to 100%. Now, all the probabilities are going to be between 0 and 1, and the probability could be 0 and 1. A 0 probability would mean that there is there is 0 probability that it's going to happen, not even a little, but 0 probability. And 1 is a 100% guarantee. Those are often rare. And let's jump into it. Let's get some practice in. So let's say that we're tossing a coin, a fair coin, and we want to know the number of heads that we could get in 3 tosses. Well, we have a few options. We could get no heads in 3 tosses. That's certainly possible. We could get 1 head only, 2 heads, or 3 heads. Those are our options. And I'm going to write out the sample space here. And we can see that we have quite a few combinations. We have head, 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 tail, head, tail, head, head, tail, 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 head, head, tail, head, tail, 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 head, and tail, 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 giving us a total of sample size of 8. Now, that when we talk about probability of getting 0 heads, that's what x is, the number of heads. When we talk about the probability of getting 0 heads, how many of them have 0 heads? Well, this is the only combination here that has 0 heads, so that's a 1 in 8 chance of spinning flipping a coin 3 times and getting no heads. How many times is there exactly 1 head? Here's 1, 2, 3 of them. That means that there's a 3 in 8 chance of getting exactly 1 head. 2 heads, exactly 2 heads. So 1, 2, 3. So again, there are 3 out of 8. And getting all 3 heads, there's only 1 chance of that. Now I want to point out, when I add up all the probabilities, 1 plus 3 is 4, plus 3 is 7, plus 1 is 8. That's 8 over 8. That exactly adds up to 1. And that leads into here, where when I add up all the probabilities, it should exactly equal 1 every single time. That should always be it. In this column, I'm going to put x times p of x. So I'm going to actually multiply across. Multiply across. Multiply across. And when I add all those up, 3 plus 6 is 9, 9 plus 3 is 12, 12 over 8, 12 divided by 8, I get 1.5. This is what's referred to as the expected value. Meaning, if I run this experiment of flipping a coin 3 times, like 1,000 times, 10,000, 100,000 times, what would I expect? I would expect the average number of heads to be about 1.5. And you can see that makes sense. It's right in the middle there, between 1 and 2 heads. And you can see that's the bulk of it there. And I'm going to graph this. And I'm going to use a little help here. So this is going to be 1/8, 2/8, and 3/8. And you can see for 0 hits, use my Starbucks card here. That is for 0 top. These are heads. And for 1 and 2, I'm going to go up to these both go up to 3/8, 1 head, 2 heads. And then we have with 3 heads. And you can see that this is very normally distributed. We haven't talked too much about what I mean by that. Low and low, and the bulk of it is in the middle, and it makes sense that 1.5 would be right in the middle here, because this looks very symmetric to me. This is a common shape that we're going to run into often. Next up, we have the mean and standard deviation. I'm not going to focus on the standard deviation. I'm going to mostly focus on the mean, which is often called the expected value. Once again, I wrote that out. Expected value. And you can see we're adding up x times its probability. And that's going to give us our expected value. This is best explained with practice, a little bit of practice here. So we have a lab that orders a shipment of 100 rats a week for 52 weeks a year from a rat supplier for experiments that the lab conducts. Prices are as below. So this means 20% of the time, the shipment only costs $10. 30% of the time, it costs $12.50. And half the time, or 50% of the time, it costs $15. So if they want a budget for this, what they need is an average, or the expected value it's going to cost each week. So the expected value is going to be 0.2 times 10 plus 0.3 times 12.5 plus 0.5 times 15. And that's going to give me a value of $13.25. So this is the average that we would expect it to cost each week. Now, sometimes it's going to be a little more, sometimes it's going to be a little less. So how much will it cost for the year? Well, that's going to be 52 weeks in a year, times 13.25. So 52 times 13.25. So $689 per year. So that's the budget for the year. Let's try another one. We have the expected value. In this case, these are calculators sold, so 10% of the time there's only 2,000 sold, 30% of the time 5,000, 40% 10,000, 20% of the time 20,000. So once again, which gives us a total of $9,700 calculators. So this is what we would expect within a year to sell. Sometimes it's quite a bit more, sometimes it's significantly less, but right around this area we can see the major bulk of it's going to be right in here. Now the profit is going to be, they make $20 profit per calculator, so that's going to be 20 times 9,700. Times 9,700. So that's $194,000. $194,000 is the type of profit that they would expect to make for that. So this brings us to somewhat of a different take on it. So we have a life insurance company, and they sell a $120,000 one-year life insurance policy to an 18-year-old female for only $150. The probability that she survives the year is quite high. So we're going to talk about the expected value, what it means, and then at the end, if there are 12,000 policies, how much would they expect to make? So this gets a little tricky. So if she lives, then the company has made $150. And the probability for surviving is 0.999356. Now if she dies, the company's down. Now here's where it gets a little tricky. The company only has to give out $119,850. It's the 120,000 minus the 150, because if she gave us the $150, we're giving it back to her, so we're not making anything on that. And the probability that she dies is going to be the complement of this number here. So 1 minus 0.999356. And when we multiply those numbers across, and by the way, when we add these up, that adds up to 1, as it should. And when we add these up, we get an expected value of $72.72. Again, this is the expected value. Meaning, all these women that are getting this, they're going to live, they're going to live, they're going to live, they're going to live, and then one will die. And so overall, this is what they expect to make overall on each policy. And there are 12,000 policies. So 12,000 times 72.72. So the only tricky part is that you got to subtract that off. It's not going to let that count. We have a couple more here. Suppose that you buy one ticket for $1 out of a lottery of 1,000 tickets, where the price for winning one ticket is to be $500. What's your expected value? Well, if you win, you only win $499. If you lose, you're out $1. The probability of winning is 1 out of 1,000, quite low. Possibility of losing is 999 out of 1,000, quite high. So when you multiply this out across, you get 499 over 1,000, negative 999 over 1,000. Again, this adds up to 1. When you add this up, you get 500 negative over 1,000, which is negative 50 cents. That's your overall expected value.